Hello everyone, I'm Aaron Dolan and I'd like to welcome you to the first experiments. This is a series of short videos designed to get you started as quickly as possible. We will breadboard working examples, briefly touch on the theory of operation, and generally provide enough information to get you started with the design, with real circuits that you can build today to put that theory into practice. In today's video, we're going to focus on the operational amplifier, specifically the inverting amplifier. Our objectives are to explore the circuit operation, to touch on the mathematics, and then to show the circuit performance using a function generator and oscilloscope. Here's a picture of that op amp installed on a breadboard. We're using an LM358 op amp, 2 capacitors, and 2 resistors. This is the schematic. You'll notice that the op amp is broken into 3 different pieces. Part A is unused, and we are grounding pins 2 and 3. Part B of that dual op amp is connected with pins 5 and 6 as inputs, 7 as an output. And finally, the part that folks often forget are the power connections. Pin 8 is connected to 5 volts DC, and pin 4 is connected to negative 5 volts DC. Finally, we have the 2 resistors. R2, which is the 100K, is known as the feedback resistor, and R1, which is 10K, is known as the input resistor. As far as the breadboard is concerned, this rail here provides negative 5 volts DC, whereas this rail up here is providing 5 volts DC. And the last thing to note is that this rail here is ground. By the way, just ignore these. They are not important. In fact, you may be better off just to scrape them off the breadboard entirely. At any rate, you can see that pin 2 is connected to ground, pin 3 is connected to ground, pin 4 goes to that negative 5 volts, pin 8 is connected to 5, and finally pin 5 is connected to ground. The bypass capacitors are connected here, with this one bypassing the 5 volts to ground, and this one bypassing the negative 5 to ground. Here's that 10K ohm resistor, which we called Rin, and here's that 100K resistor, which we called RF, for R feedback. And it is providing feedback because it's taking the output, which is on pin 7, and you can see it loops back to pin 6. Here it is again. The output on pin 7 loops back to pin 6, providing feedback, and then the input is on R1. Moving on, the math for this circuit is relatively simple. The gain of this circuit is negative RF divided by Rin. So you can see that for this circuit, the gain is negative 100K over 10K, which gives you a total gain of simply 10. Momentarily, we'll show that this is the case when we use the function generator and oscilloscope. Before leaving, we should note that this gain equation is true all the way from DC up to some maximum frequency, which is dependent on the amplifier type and on the gain. Identifying this maximum frequency is beyond the scope of this introductory video, but it is certainly something we can explore in a future video. Now that we know a little bit more about the circuit, let's go ahead and test it using the Digilant Analog Discovery. You can see that I'm using one of the older devices. In fact, this one is affectionately known as the legacy type. However, it still shares many of the attributes of the newest edition. It serves as a waveform generator, an oscilloscope, and a power supply. We'll be using all three of these functions in the experiment. You'll notice there are 6 connections. This is 5 volts positive, providing power to this upper rail. This is 5 volts negative, providing power to this rail. The black wire is ground. This yellow wire is the waveform generator. And then the blue and the orange are the oscilloscope channels, with orange as channel 1 and blue as channel 2. Here you can see that the yellow wire, which is the output of the waveform generator, is connected to channel 1. So we are monitoring the physical signal going into the op-amp, and we'll be looking at the output on channel 2. If you look carefully, you can just make out the I/O for this analog discovery. For example, 1 plus is channel 1 of the oscilloscope, 2 plus is channel 2, W1 is the signal generator, ground is this arrow here, and the plus and minus power supplies are right here. This is the Digilant Waveforms software. Let's start by turning on our power supply. So supplies, and here you'll see that the master enable is off, so we're going to go ahead and push this play button. That activated the plus and minus 5 volt supplies. Go back to welcome. Let's add the waveform generator. It's currently set for a sine wave at 1 kilohertz with 200 millivolts output. You'll notice that goes from 0 to 200. So when it gives you 200 millivolts, that's a peak. And then let's add the oscilloscope. And we're looking at 2 channels, with channel 1 being the input. And you'll notice that it's very close to 200 millivolts. You can see right here on the side. And then we'll turn channel 2 back on, which is the output. And you can see that it's providing approximately 2 volts peak. For ease of viewing, we can click this button here, and it'll show all the windows at one time, with the oscilloscope on top, the power supplies here, and the waveform generator here. Let's go ahead and drop this down to a very low frequency. For example, 1 hertz. We'll set our time base to something more reasonable. So now we're looking at a 1 hertz waveform, 200 millivolts in. Again, that's a peak. We can see that in the oscilloscope right here. So 200 millivolts is this point. And we can see the output is inverting with a gain of 10. So we're approximately 2 volts peak and 2 volts negative peak. Let's go back to 1 kilohertz. Adjust our time base again. And now I wanted to show you what clipping looks like. So if we take our input and we set it to 1 volt, the input will be 1 volt. You can see here that it goes up 1 volt, down 1 volt, right, with the scale right here. However, the output will not do that, because the output will be clipped. Remember, this has a gain of negative 10. So if you put in 1 volt peak, we're trying to output 10 volts peak. However, the power supplies are limited to plus and minus 5 volts, so we're never going to get there. So instead, you end up with this clipped waveform. If we lower the input back down to 200 millivolts, now we're attempting to output a 2 volt signal, which it does quite nicely. One of the other things I wanted to show you is what happens when we go to higher frequencies. Here's 5K. Everything looks pretty good. We go to 10K. Everything still looks good. 20K. 50K, you can see something's gone wrong. The amplitude is now reduced, and what was a nice sinusoidal output has become what looks like a triangle wave. This is known as slew distortion. Basically, the op-amp is not capable of moving fast enough. So you don't get a sinusoid, you get what looks like a triangle wave. If we were to push that further, say 100 kilohertz, it gets worse, and 200 kilohertz, the signal is down considerably, and it looks nothing like a sinusoid at all. There's a couple of ways we could fix this. We could lower the gain, but that gets into something called gain bandwidth product that is a topic for another video. Another option is to replace the op-amp with something that is pin compatible. And that's what we'll do now. We'll replace the LM358 with an LF412. Let's go ahead and turn everything off using this button. So you can see down here that the master enable is off. And I'll replace that op-amp really quickly. Now that that's in, let's turn everything back on. I don't know if I mentioned this already, but oftentimes op-amps are pin compatible with each other. So I was able to change that LM358 with an LF412 without making any modifications to the circuit. At any rate, you can see that that LF412 op-amp is a little bit better because the gain has come up and that triangle distortion is gone. However, 200 kilohertz is still too high, as is 100, and I think it's safe to say that this particular circuit tops out somewhere around 50 kilohertz. Perhaps we could improve that again if necessary by using an improved op-amp, or as I mentioned before, we'll address this limitation in another video where we talk about the gain bandwidth product. That's all for now. I do hope you found this video useful. Please leave any comments, questions, or concerns in the space below.